Hello, this is the Chapter 2 lecture notes on solar radiation and the seasons, and this is Dr. Rudabaugh, and hopefully I'll be able to highlight some key themes you'll need to complete and understand this chapter, and also do the Sun Angle Lab that really examines why places around the world have different seasons, so the very use of the terms summer, winter, fall, spring. We're really going to get why, depending upon where you live, has a massive influence on influencing the way in which you experience the seasons. And that's why if you live in central Illinois, the idea of summer or winter could be very different depending upon whether you lived in Australia, and just the very way in which we define how the seasons proceed and the types of temperatures we expect and why they're different across the planet is what we're going to hit upon in this chapter. So it's I really like chapter 2. I really enjoy understanding the seasons. When you look at monuments like Stonehenge, or if you go to Cahokia Mounds in southern Illinois, we realize that humans for thousands of years have been trying to build monuments either made of stone or wood, or maybe even the pyramids in Egypt, to track the movement of the sun and try to understand the movements in the sun and how they give us a sense of time of year. And that's what we'll be doing here in chapter 2. So our key is we first have to accept and understand that solar radiation is the ultimate engine that drives everything in weather and climate. The energy from the sun and how it gets to the earth is ultimately what is the engine that drives weather and climate. So when you try to figure out any process with weather and climate, you really have to begin and understand how the energy of the sun moves. And what we will discuss is how basically the sun's energy and radiation is not equally shared. Energy itself can be described in a variety of ways, whether we talk about kinetic or potential energy. And the kinetic energy is kind of what we talk about more in this class, is the energy from the sun, and the radiation is what gives molecules movement. And all forms of kinetic energy, whether it's electricity or making water move a paddle wheel, or watching heat move through water and water boiling. And what we're going to lock in is radiation from the sun is the energy that causes movement in matter and molecules. And kinetic energy is obviously what we'll spend more time on. Whereas if you were in other areas of science, maybe in physics or chemistry potentially, you could talk about forms of potential energy. You know, one of the most famous is the energy that is stored in food and only becomes energy upon digestion, or the energy stored in firewood and only becomes released until you light it with fire, or a battery. Potential energy and kinetic energy are two forms of energy, but obviously we're going to really lock in on the energy of the sun and the radiation of the sun to really excite and move molecules, and that's what makes us have measurable temperature. And obviously the temperatures and the seasons in the Midwest of the United States will be very different than somebody who lives in Australia near the equator. Kinetic energy is basically, for us from an atmospheric perspective, the molecular vibration that occurs when molecules interact and absorb or scatter radiation from the sun, and that causes the molecules to vibrate. And the more energy they absorb, the stronger the type of radiation they absorb, the more vibrations and kinetic energy they will have. And so that's what we're going to understand, is how effectively the sun is basically through different mechanisms, primarily through the angle of the sun hitting the earth, will basically give different areas of the earth more or less kinetic energy to move the molecules in those areas. When energy is moving, there is a variety of ways in which we could talk about energy moving, and we could talk about conduction and convection. And when we talk about conduction, we're often talking about molecules moving in solids, and because solids are in contact with one another like brick, if you have one side of a brick and you heat it, it will obviously, through kinetic energy, can actually move through vibrations. One molecule touching another molecule will cause the molecules to start vibrating. Whereas convection occurs because when something is heated, it will rise and become less dense and transfer energy often upwards. And I would give you a good example to understand how convection would work is put convection in a water tank. And it's a lot of good YouTube videos you could find and watch energy transfers as they'll heat one side of water and put food coloring in it. And you'll watch how and usually that side of the tank has red food coloring, and the red food coloring will rise up through, and on the opposite side they'll have blue food coloring, and you'll actually watch the blue food coloring on the colder side of the water tank cool, and you'll actually watch energy transferring from hot to cold, and you'll see white and red and blue streaks moving. And when you're flying or seeing a bird moving up through the air and it's rising, you can often see warm air rising off the ground with convective processes in a bird of prey like a hawk lifting up through the air, which is a good example of convection. And these are all ways of how the earth moves energy from the earth's surface and begins to move it upwards. One of the key ways in which we have to move heat, though, or move energy, is radiation. The sun transmits most, if not all, of its energy to the earth in the form of electromagnetic waves, which we call EMR. And these electromagnetic waves that come into the earth's atmosphere from the sun travel in a variety of spectrum. And we measure these waves by the height of them and how close the waves are together, which is the frequency. So we talk about energy from the sun and what we call short wave or long wave. Short wave radiation is where the waves are very close together, and that gives them a high frequency. And waves that are longer and further spread apart are long waves and have low frequencies. And effectively, electromagnetic radiation is one of the ultimate ways in which energy from the sun both moves into the earth and moves out of the earth. And simply put, some parts of the earth, like we'll discuss around the equator, they will get more electromagnetic radiation, and places near the North and South poles will get much weaker or lower levels of electromagnetic radiation. The key thing to understand is electromagnetic radiation travels in a variety of spectrum. And we have ways of classifying the spectrum, again, based upon the wavelength and the frequency of the radiation. So by the way, when you're using cell phones or you're listening to the radio in your car, or you're cooking food, or you're going to the hospital and using x-rays, or you're using heat to prepare food, you're looking at how humans have basically over thousands of years have learned how to use different wavelengths of electromagnetic radiation. And we have to understand these differences because the sun is the ultimate source of electromagnetic energy, and we must understand these different wavelengths to really get a sense of how the sun's radiation is influencing the earth and driving our seasons. This chart shows you the different names of electromagnetic radiation with the strongest to the left, and as you go to the right, they become progressively weaker. As you notice, the wavelengths here start with gamma, X-rays, ultraviolet, visible, infrared, and radio. The wavelengths down here to the left are called our short waves because you could see how closely together they are, and they're considered high frequency, powerful radiation. We'll discuss here on the second video series what are called the Stefan Boltzmann rules of understanding radiation. And it's important to note that when we discuss the two primary energy emitters that we talk about that drive weather and climate are the sun and the earth. And the sun and the earth are simply much different temperatures. And one of the things that we will learn is that all objects on the earth do radiate certain wavelengths of radiation. It's one of the rules that Stefan Boltzmann describes, is that all objects in the universe with measurable temperature do radiate energy. However, depending upon that temperature, they emit different wavelengths. So the sun, being really warm, tends to produce what we call short wave or high frequency radiation, whereas the Earth is much cooler and it tends to emit more radiation down in the longer wavelengths or the long wave and low frequency radiation. And the Earth is primarily a visible, or the Earth is primarily producing infrared radiation down through radio waves. And so as a result, the Earth is kind of down in here with long wave radiation, which has low frequency, and the sun is over here on the left with the more high energy producing short wave high frequency radiation. Now I'm going to stop the video here because I want to call this, I only like about 10 to 12 minute segments, and we'll take off with segment 2. But now you're getting a working knowledge of understanding a little bit about radiation and how it's packaged up in different wavelengths.